Target-oriented dialogue, or TOD, is a key area in artificial intelligence where systems help users achieve specific goals through natural language conversations. For example, this could involve negotiating a price for a bike or providing personalized recommendations. In the era of large language models, or LLMs, these systems have advanced significantly, generating responses that feel human-like and engaging. However, LLMs often act passively, following instructions without proactively planning to guide the conversation toward the intended target. This lack of strategic planning can hinder success in TOD scenarios. The research paper introduces a new framework called DiffTOD, which stands for Diffusion Models for Target-Oriented Dialogue. The core idea is to overcome the limitations of existing methods by using diffusion models to enable non-sequential dialogue planning. Traditionally, dialogue systems generate plans step by step, like in a sequence where each action depends only on what came before. This sequential approach can lead to problems, such as compounding errors, where mistakes build up over time, and myopic actions, meaning the system focuses too narrowly on the immediate next step without considering the bigger picture. To illustrate, imagine a negotiation dialogue about buying a bike. In a sequential method, the system might respond to the user's offer of $600 by immediately countering with $300, but without fully thinking ahead, it could get stuck in a loop or miss better strategies. In contrast, DiffTOD allows for non-sequential planning, where the system can generate and refine an entire dialogue trajectory at once, considering both past interactions and potential future outcomes. This is shown in the paper's figure, which compares sequential planning, where actions are decided one at a time, and non-sequential planning, which involves look-ahead exploration to optimize strategies over a longer horizon. DiffTOD formulates dialogue planning as a trajectory generation problem. In simple terms, it treats the entire conversation path as something that can be generated and refined iteratively, rather than built linearly. It uses a diffusion language model to estimate the likelihood of different dialogue trajectories. Diffusion models, originally from image generation, work by starting with noise and gradually refining it into a coherent output through a series of steps. Here, the model applies that principle to language, denoising a sequence of dialogue actions to create a plan that's more globally consistent and less error-prone. A key innovation in DiffTOD is the introduction of 3 tailored guidance mechanisms, designed for different types of TOD targets. These mechanisms provide flexible conditional guidance during the planning process. For instance, if the target is to reach a specific price in a negotiation, one guidance type might prioritize actions that lead toward that price while accounting for user responses. Another might handle more exploratory targets, like gathering information, by encouraging diverse response paths. This allows the system to adapt at test time, meaning it can adjust its strategy based on the specific scenario without needing retraining. The paper's experiments demonstrate the effectiveness of this approach across 3 diverse TOD settings. In one setting, it might involve transactional dialogues, like haggling over prices. In another, it could be recommendation tasks, where the system guides the user toward personalized suggestions. And in a third, perhaps more complex interactions, like multi-turn problem solving. Results show that DiffTOD performs non-myopic look-ahead exploration, meaning it can anticipate future steps and optimize actions over an extended conversation. This leads to better overall performance, with the system maintaining global consistency and flexibility in handling varied and complex dialogue scenarios. For example, in a bike negotiation, DiffTOD might generate a full plan that includes proposing an initial price, anticipating counteroffers, and refining responses to steer toward a deal, all while avoiding the pitfalls of sequential methods. The authors conducted extensive tests, and the findings indicate that this non-sequential approach reduces errors and improves success rates compared to traditional LLM-based planning or reinforcement learning methods. One reason this matters is that TOD systems are increasingly integrated into real-world applications, from customer service chatbots to virtual assistants. By leveraging diffusion models, DiffTOD addresses the sequential limitations of autoregressive LLMs and policy-based agents, which often rely on Markovian decision processes. These processes assume that decisions are made based only on the current state, but DiffTOD breaks from that by incorporating broader context and iterative refinement. The paper also highlights the importance of proactivity in LLMs. While models like those from Yang and colleagues are trained to follow instructions, they don't naturally plan ahead. DiffTOD enhances this by combining diffusion techniques with conditional guidance, making it a versatile tool for various TOD challenges. The code and data for this work are available online, allowing researchers to build on these ideas. In summary of the technical details, the diffusion language model in DiffTOD estimates the probability of dialogue trajectories and uses guidance to steer generation. This involves adding noise to an initial state and then denoising it step by step, with conditions based on the target. The three guidance mechanisms are specifically designed: one for deterministic targets, like exact outcomes, another for probabilistic ones, involving uncertainty, and a third for exploratory targets, promoting creativity in responses. This customization ensures that the system can handle the diversity of TOD tasks effectively. Overall, through these innovations, DiffTOD represents a significant step forward in making dialogue systems more strategic and adaptable, paving the way for more reliable interactions in complex environments.